Hello, my name is Alpheus Madsen, and I'm doing this presentation on exploring the unseen world of ideas, the philosophies and histories of mathematics. Now, to provide a little bit of background for myself, I'm a mathematician who for the last 10 years or so has been pretending to be a software developer. I first became interested in mathematics because of an English class, actually. One of the books I saw uh, on a list of books I could choose from reading, I saw Michael Crichton on there. And so I decided to read Jurassic Park. And one of the major themes in Jurassic Park was chaos theory. And as I read about, I the book caused me to be curious about chaos theory, and so I hunted down more books about it and tried to learn more about it. And there's a particular passage that really struck me that where I'm not sure if this is a real or hypothetical conversation, but someone was talking to a mathematician named Benoit Mandelbrot, and someone asked him, "Are you aware that, or are these mathematicians aware of the mathematics that you're using for your the work you're doing?" And his response was, "No, and they probably don't care." And there was something that really struck a chord in me about the idea that you could do mathematics and not care about whether it's applied, but you do it just because of the beauty of it. And so, um, with the exception of one time where I seriously questioned whether I had made the right decision and becoming a mathematician, I decided from that day that I'd be a mathematician, and I haven't had any regrets since. Well, I guess I do have one regret, in that I haven't been able to pursue mathematics the way I would like to do after I finish graduate school. And so, one of the interesting things about mathematics is that it's very deeply tied to philosophy. And there are some very important reasons for this. There are some very important philosophical questions, such as what is truth, and what does it mean for truth to exist? And why is mathematics so good at describing the world, or is it? And what is beauty and what is elegance? These are questions that are very important for mathematicians, but they're also important for philosophers. And when I was an undergraduate, one of the things I did in my statistics class was do surveys about interest in mathematics versus in STEM fields versus humanities fields. And one of the things that I found interesting was that philosophy majors, even though if they struggled with mathematics, nonetheless appreciated mathematics for its beauty and ability to get into truth. And in this particular presentation, I'm not necessarily going to address these particular questions, but I am going to try to go over the history of mathematics and how it ties into philosophy, and give a brief overview of some modern thoughts about what about what mathematics is. And it's going to be very difficult to cover this because it is a very broad topic, and it literally goes back to 3 or 4 thousand years of both mathematical and philosophical thought. So the first I'm going to talk about the origin of mathematics, and it actually kind of originates in an interesting place, and it's not just the origin of mathematics, but civilization in general. Back in the early Babylonian days, the Babylonians were shepherds, and uh, they needed a way to keep track of how many sheep they had when they sent them out of the pens and did their grazing and then they brought them back. And so one way the way they settled on doing this was having a little basket where they'd put pebbles in each sheep left, and then move the pebbles into another basket as they came back. And they started creating contracts for deals by creating these little round balls where they'd put pebbles in them to represent sheep. And after some time, they started using those pebbles and putting the dents in these contracts, so they wouldn't have to break them open to see what's inside. And gradually they stopped using these little clay pockets or envelopes, and they just um, made the tablet flat instead. and started putting little markings on these, and these little markings became a writing system. And this in particular is cuneiform, but cuneiform gradually became simplified into an alphabet, and basically everything, both writing and mathematics, comes from this desire to count sheep. And the Egyptians, in particular, were known to use both the Egyptians and the Babylonians quickly learned that they could use numbers and mathematical principles to do major things, such as build a pyramid. And in fact, one of the techniques they would use to make sure that they'd get a right triangle is to tie units into a rope, and then make a triangle that's a size 3 by 4 by 5. And while they didn't have the Pythagorean theorem yet, they knew that that triangle necessarily had to be a right triangle. And a Greek named Thales of Miletus was visiting Egypt one day, and one of the things he noticed was that every time an Egyptian would come across two lines crossing each other, they would measure about the opposite angles and see whether or not they were equal. Well, Thales looked at this and he realized that these two lines, they have certain properties that straight lines always have, and the angles have certain properties that angles always have. And so you could reason that since the two lines, they have an equal halving, or an equal angle going from one side to the other side of the point of intersection, that they share this this angle between the two of them. In this particular diagram marked with the Greek letter theta, that the two Greek letters alpha and beta in light blue necessarily had to be equal. And this was the very first mathematical theorem to be proven. And Thales had gone on to prove several more theorems. And by this, Thales became the first mathematician, as we know of mathematics today. And so the Greeks in particular grew and became created philosophical thought. And while I can't remember off the top of my head who the first philosopher was, Pythagoras is in particular remembered for not just for developing mathematics further, but for developing a very a reverence for mathematics that became sort of a religion. And one of the things they've found a lot of harmony between mathematics and nature, and they came to really respect numbers and numbers and how they're tied to mathematics. And their proofs, however, depended on the idea that any two lengths of line can be equally that for any two lengths of line you could find a second or a third line that could divide up the two lines equally. There was one mathematician, however, named Hippasus, who looked carefully at the square root of 2, and he concluded that if you assume that it's possible to find two such lines, then try to make that represented the square root of 2, that those two lines would necessarily basically he created a rational function or a rational number, and showed that rational number would have to be that rational number would lead to a contradiction, and therefore there could be no such little segment. Now, there are many legends as to why Hippasus was thrown overboard, or even whether or not he was. But some say that he was thrown overboard for discovering this and ruining a lot of proofs of Pythagoras. Others say that he was thrown overboard for revealing this to people outside of mathematics. and others say he was thrown overboard for reasons independent of this. But regardless, this is something very controversial because it completely threw out a lot of the proofs of Pythagoras, and they kind of had to start from scratch. Now, after Hippasus, there's Euclid, who is famous in particular for creating a book that we call Elements or the Elements of Geometry. And he took several of the works of mathematics in his day, and he distilled them to the fundamental idea of starting off with a few unproven axioms, a small number of definitions, and a small number of undefined terms, and then using those terms to build up all of mathematical thought. Now, one of the things I've noticed in looking at elements is that rather than completely throw out the proofs of Pythagoras that depended on the ability to divide up lines equally, they actually became theorems, but they became theorems for what we'd probably call number theory today, and basically talking about integers and fractions. And that he also developed a theory of irrational numbers independent of that tried to address numbers like the square root of 2. Now, along the same time, Plato these ideas drew the attention of the attention of modern day of the philosophers of the day. Plato, in particular, looked at mathematics, and he saw the amazing beauty of it, and how it could be developed in such an independent way, in such a pure way. Unlike pretty much under any other field of human thought, mathematicians can create something true and create it out of their mind. And he personally looked at this and concluded that this entire world, that when mathematicians think about these things, they think about these ideal things that are independent of reality and exist in a world of ideas independent of physical reality. And not all philosophers thought this made sense, though. Aristotle, in particular, looked at this and said first of all, what Plato, the idea that Plato has that you have this pure world with pure ideas that is somehow independent of reality yet tied to reality, and that reality is a shadow of it, is nonsense, because you end up developing this infinite relationship between reality and these forms that are in this abstract world. And that one of the classic examples is the perfect idea of a chair versus a physical chair. And that if this independent world of ideas exists, then there would have to be these infinite relations between the perfect chair and the real chair, and the relationship between them, something that's kind of in between those, and so forth. So he viewed that there's only reality, and that's the only thing you need in order to understand the world. And in some ways, although these two philosophies are very old, they also kind of represent the two major conflicts between how people view mathematics even today. So one of the important ideas of mathematics actually came about through someone named Zeno of Elea, who looked at some of the thoughts that mathematicians have been developing, such as the idea that between any 2 points there has to be a point in between, and he had a hard time accepting some of these basic axioms, and so he developed what became known as Xenos Paradoxes. And one of the classic examples of this these paradoxes is the tortoise and Achilles. He suggested that if it's possible to have an infinite number of points between 2 points, then in a race between a tortoise and Achilles, giving the tortoise a head start, however big or small of a head start you want, Achilles would never be able to win the race because the tortoise would start moving, and in order for Achilles to win the race, Achilles would have to run up to the point where the tortoise had been before. But in the meantime, the tortoise would have moved a little bit further, and so Achilles would have to run up to the tortoise and to where the tortoise's new point, and then the tortoise would have moved a little further more, and then Achilles would have to move a little bit further than that, and this kind of thinking opened the door. Really proved to be a challenge for mathematicians, and they had to try to come up with ways to address these paradoxes. And in some cases, or in some ways, mathematicians and philosophers of the day were able to address it, but not everyone accepted those explanations. And even today, it's argued that calculus and the idea of limits and the idea of figuring out how to take an infinite sum and sum everything up into a finite number would address these notions. But even today, there are people who say that calculus isn't sufficient to address these paradoxes. But regardless, paradoxes like this allow mathematicians and philosophers to really think about the fundamentals of mathematics, and then whether or not our thought processes make sense. And another example of what many mathematicians might consider, well, they never really considered this a paradox, but in some ways it was, and that is something called addressing something called Euclid's fifth postulate. And basically, Euclid's fifth postulate says that when you have two lines crossed by a third line, and the angles of the two lines add up to less than 180 degrees on one of the sides of that crossed line, you could expect the other two lines to meet at a point at some point. And the reason why this particular postulate drew the attention of mathematicians is that for centuries mathematicians had looked at this and said, this is a really complicated postulate. It's not simple like between two lines or between 2 points on a line you could find another point. It sounds more like a theorem. And so for centuries mathematicians tried to prove this. And Carl Friedrich Gauss in particular, along with a couple of other mathematicians of his day, ended up deciding to try to prove this by something called proof by contradiction. Essentially, the mathematician would assume that something that they want to prove false to be true, and show that by assuming that it's true, something absurd ends up happening. To go back to the hypothesis demonstration that the square root of 2 is irrational, for example, he assumed that p over q, but the fractional form of the square root of 2, would have to be in its lowest terms. But then he showed that because it's equal to the square root of 2, both p and q would have to be even. But that contradicts the idea that they're in lowest terms, because that means that you could factor out 2 from both of them. And that's the contradiction. In the case of Carl Friedrich Gauss, he tried to show that two lines that come closer and closer together necessarily would have to intersect, by assuming that they'd intersect, they would never intersect. he assumed that that would lead to a contradiction. But the more he tried to prove a contradiction, he proved theorem after theorem after theorem, and eventually um, he concluded that he wasn't going to come to a contradiction. Instead, he developed an entirely new a new geometry that seemed consistent in much the same way that Euclid's geometry is consistent, but it was a completely different world. For example, in this particular world, it was possible to have two lines that met each other at a point, but a third line would be parallel to both of them. Whereas in Euclidean geometry, if two lines came to a point, a line would have to be parallel to either one or the other. It would intersect the other line. So he ended up he was already involved in other mathematical controversies during his lifetime, so he never published this. But about 20 or 30 years later, another mathematician, the son of another mathematician's friend, had tried to do the same thing, and he came to the same conclusion. And Carroll said, "Well, this is interesting. This is something like I did 20 years before," and he showed him his work. And so this particular geometry had ended up not being called after Gauss, but after Bolyai or after Lobachevsky, who came up with the same ideas in Russia a couple of years before as well. But because he was in Russia, he ended up publishing his results in an obscure journal. And this particular when this kind of geometry came out, it sent shockwaves through the mathematical world, because it asks questions. Can we prove that things are consistent or inconsistent, or what's true? If we could change these axioms and come up with new geometries, what else can we what can ultimately can we prove? Now, I'm going to bring up Lewis Carroll, who wrote a little short story called "What the Tortoise Told Achilles," going back to Xenos Paradoxes. And this little essay is kind of interesting because although he didn't have much to say about these new geometries, and in fact he wrote a little play called Euclid and His Modern Rivals that addressed modern geometry books that were coming out that were intended to replace Euclid's elements. And he was firmly in the camp that Euclid's elements did not need to be replaced, and that all these new geometry books are actually kind of either were about the same as Euclid's elements, or they weren't as good as Euclid's elements. And he had the short story of Achilles, what Achilles said to the tortoise, though, he actually had an interesting idea about logic itself. Basically, in the little essay, he shows how logic depends on us assuming things without proof, and that there's no way that we could accept logic itself without necessarily proving it. That basically he showed that at some point we have to take the axioms of logic or even the foundations of logic on faith and accept it and build our mathematical thought from there. So a couple of other mathematicians around this time, or actually more closer to the turn of the century, Carl Friedrich Gauss was did his work in the 1830s to 1850s, whereas Hilbert and Russell did their work in the late 1800s or 1800s, early 1900s. So around the turn of the 20th century, I should say, they decided that they wanted for once and for all to put mathematics on a firm foundation, a logical foundation, one that could be that really didn't even need human intervention, that could somehow generate mathematical theorems almost automatically. And they decided to do this by something called set theory, where basically the only elements are things called sets, and whether or not something is a member of a set. And it's a very simple way to generate mathematics, and it's something, but it's also a very tedious way to do it. One of the works that they've created, I think it's called the Principia Mathematica, if I remember correctly, actually builds up mathematics from very simple principles, and I think it takes something like 100 pages to get to very foundational principles like 1 + 1 = 2, or between 2 points between 2 points on a line there's a point. So that kind of program is not for the faint of heart. But the reason why Bertrand Russell is interesting is that even with something simple as set theory, it was prone to fairly simple paradoxes. In the case of Bertrand Russell, what's known as Russell's paradox, you have the question of what does it? Suppose you had basically, he asked the question: suppose you had a collection of sets that include all sets that do not reference themselves. What set does this particular set belong to? Well, if it's not a member of itself, then obviously it belongs to itself. But if it belongs to itself, it cannot be a member of itself. And so, actually, this is kind of similar to another paradox that I've heard described called the barber's paradox, where a barber puts up a sign in front of the shop saying, "Every man in the village who does not shave himself comes to my shop for shaving." And I brought this up because the question is, who does the barber shave? Does he shave himself or not? Well, I was talking to my kids about this in this particular paradox, and my wife said, "Oh, I know the answer to this question. Who said the barber is a he?" Well, technically, that wasn't supposed to be the resolution of the paradox, because the barber was supposed to be a man, but actually, this is how the mathematicians resolve Russell's paradox. Anyway, they basically say that some things just cannot be a set, and the set of all things is one of those things. And similarly, Russell's set of things that do not include itself cannot be a set as well. But basically, things like this really forces us to sit down and think. What is valid and what's not valid, and what can we do to make sure that we never get invalid things? Well, in the efforts to try to create, I guess you could call it the mathematical theory of everything, that and in particular, not just the mathematical theory of everything, but something that could prove itself purely consistent within itself, and so that you could have complete faith, just complete faith, complete trust that the mathematical system is valid and solid. A mathematician named Gödel came along and proved what's called the incompleteness theorems. He proved two things. The first one is to prove that a mathematical system that is sufficiently complicated is going to have things that within the things that cannot be proven in that mathematical system, both true things and false things that are that we'd consider obviously true and obviously false, and they'll be beyond the reach of the axioms. And what's more, he also proved that anything something simple enough to contain basic arithmetic is going to be complex enough to not be able to prove everything inside the mathematical system. And the second thing he proved is that one of those things that will never be able to be proved within the mathematical system is the consistency of that theorem. Or not the theorem, the consistency of the system itself. So you could always show that something is consistent by embedding it in something that has already been proven consistent. For example, one of the things that has been shown to, or one of the ways that non-Euclidean geometry that Carl Friedrich Gauss had been developing was to take that geometry and embed it to Euclidean geometry, where the lines were either straight lines that went through the circle of, or is to take a circle, and if a line went through straight lines that went through the center of the circle, and circles that were tangent to the chosen circle boundary, the circle as well. And those form when you match up the theorems for that mathematical system to Friedrich's, or to Gauss's geometry, you have a one-to-one correspondence, and therefore you can prove that if Euclid's geometry is consistent, then this weird hyperbolic geometry also has to be consistent. However, you cannot prove that Euclid's geometry is consistent using its own axioms. You'd have to prove it by embedding it into something bigger than that. But then you'd have that problem that bigger thing is inconsistent or it cannot prove its consistency as well. And so an interesting observation that some mathematicians have made since then is that if a religious system is a system that you have to accept in faith and cannot be proven to be true, then mathematics is the only religious system is the only system of thought that has proven itself to be a religion. And while this is Kurt Gödel has basically put an interesting wrench into Hilbert's program to try to create this the system of all truth, and so it has caused many mathematicians and philosophers to ask themselves, what is true? And one of the another interesting paradox that I learned about as an undergraduate, but still fascinates me to this day, is something called something proven by Stefan Banach and Alfred Tarski. One of the controversial axioms in mathematics is called the axiom of choice, and some mathematicians dislike it and can't stand it. And these two mathematicians didn't like it, and so one of the things that they did was to prove what's called the Banach-Tarski paradox. And what it says is that what the axiom of choice says is that given a set, you don't necessarily have to have an explicit rule to be able to choose a point from that set. Or, for example, or one good example that I like to use to describe this is, if you have an infinite number of drawers of pairs of shoes, you could say you can easily say from every drawer, pull out the left shoe. However, if in those same drawers you also have a pair of socks, you cannot have a rule to say from every drawer pull out a sock, because the two socks are identical, unless you use the axiom of choice, which says, yeah, go ahead and pull out the sock. And the reason why the Banach-Tarski paradox is so disturbing to our intuition is it says that you could take a sphere, and you could there are actually two versions of this. One is you could take a sphere, you could cut it up into 9 pieces, and just using translations and rotations, you could shift those pieces and then put them back together and form 2 spheres of the same size. The other form says you could take a big sphere and cut it up into thousands of little pieces. I think something like 59,000. Although it's a huge number, it's still disturbingly finite. And you could take those pieces, and again with just rotations um, rotations and slides and translations, you could put them back together to form a little teeny sphere the size of a ping pong ball, or when you started off with the size of a basketball, or vice versa. Now, the problem with the axiom of choice, though, is that accepting one of its alternatives means that you have to abandon some certain nice things as well. One of those nice things is if you have what's called a vector space. It's nice to be able to have, for example, the three-dimensional space. You could choose three independent vectors that you could use to create, or basically three independent directions that you could use as a coordinate system to identify any point in that space. And the axiom of choice allows us to be able to take any space like that and create some sort of coordinate system. However, if you don't have the axiom of choice, then you can have spaces that do not have coordinate systems, which again is kind of on the weird side. So it becomes the question of what kind of weird side effects do you want to have? And there are entire field of mathematics where the axiom of choice isn't just a nice thing to have, it's absolutely crucial. So this brings us to some modern philosophies of mathematics. The first one is Platonist. This one goes all the way back to Plato, as I described, and it's an idea that there exists an entire world of ideas that we access with our mind, and there are many mathematicians, and I'm one of those mathematicians actually who can't help but believe that this has to be true, that our axioms of logic and mathematics actually helps us understand a true world, a world that's completely independent of us and true independence of thought. Now there's one step away from that called nominalists, who believe that there isn't this world of ideas. However, mathematics is based on a fundamental mathematics is tied to the physical world. For example, simple counting is the development of being able to put pebbles in a basket, and nominalists have to admit that while this has a certain appeal to it, that also has a disadvantage in that it cannot admit rules. It cannot admit things like, or it has a difficult time admitting irrational numbers, which are merely numbers that you could have which are numbers that have that necessarily have to just be approximated. You could approximate them to however refine of precision you want, but you nonetheless are stuck with a certain amount of finiteness. But nominalists admit that they especially struggle with the ideas like the square root of -1 that don't necessarily have a physical counterpart to it. And even if it did have a counterpart, you could always, the square root of -1 fits in the rotations of the planes. It's very easy to keep on finding more and more numbers that don't have it's hard to say that they have a physical counterpart to the real world. And even if they did, it's interesting that these numbers are often discovered independent of a physical phenomenon. The square root of the imaginary number, which is the square root of -1, for example, came about not because of of mathematicians trying to work out a nice way to put points on a plane. They came out because mathematicians were trying to find roots to the cubic, and they came out with a cubic equation that's kind of like the quadratic formula that we learned in high school algebra. However, it is a whole lot more complicated, and it has this disturbing side effect that in order to find real, genuine roots of a cubic, um, you simply have to pretend that that you could take the square root of a negative number and just work out the mathematics until you get that real number, because these imaginary numbers eventually cancel themselves out. And it took a few decades after doing this, or maybe even just a couple decades. I can't remember the timeline off the top of my head. But eventually, mathematicians saw that number and said, "Well, what happens if we play around with that number and discovered that it's a number in its own right?" So then you have the intuitionists and the constructionists. They believe that that mathematics is not a real thing, except that it's something that we construct in our heads. And when we take that construction and put it on a piece of paper, that is something that another mathematician will look like and reconstruct what the first mathematician did in their heads. And the intuitionists are interesting because they don't believe in things like the law of an excluded middle. They would say that that a theorem like that like something called a Riemann hypothesis, which has a prize out for the mathematician who proves it true or false. They would say that it's neither true nor false right now because it hasn't been proven, and so it hasn't been properly constructed in some mathematician's head. And constructionists run into problems because of their philosophical stand. They don't allow the construction of, or they don't allow what's called existence theorems. For example, they cannot they cannot accept the idea of a proof that for example, there's an important theorem that says that if you have a set with an infinite number of points, that it's closed and bounded, so you could put a circle around it, for example, then you could eventually find what's called a point of accumulation, which is a point that's guaranteed to always have infinite points around it. Now, to prove this, you'd have to put smaller and smaller regions around that point until you and show that point has to exist as you go down infinite number of sets. But there's no way to actually construct that particular point, and that particular theorem is foundational to many fields, and and so mathematicians aren't willing to give up that much mathematics to be strict constructionists. Formalists and fictionalists are mathematicians who believe that mathematics isn't real. It's just manipulating symbols on a paper, and we have these rules, and we're basically playing a game, manipulating these rules and coming up with theorems based on these things. And fictionalists will go so far as to say that mathematics has no connection to the real world at all, that it's possible to do science without mathematics at all, and that it's just that mathematics is just a convenient fictional shortcut that allows us to focus our thought. And I want to say finally, but there are actually more schools of thoughts than these. These are just some of the more common ones. You also have conventionalists who believe that everything that we do in mathematics is just a convention. That when we teach mathematics to our children, for example, that 5 plus 7 is equal to 12, we're teaching them a convention, and we don't necessarily abide by that. We don't necessarily need to abide by that convention. And we could teach them. We could, if we wanted to, we could teach them a new convention, and then that would generate a new mathematics. And so these are all attempts to, in some way or another, to try to describe where mathematics comes from, and why mathematics describes the world, or even if it does. And one of the things that I would like to point out is going back to reality, because in some ways all this originated back from Babylonians and Egyptians trying to keep track of sheep and grain and build giant pyramids and other structures. Well, one of the things that has been observed by at least a couple of people is the idea that we have mathematics because of solar eclipses. And solar eclipses are so astounding that if you see one, you want to be able to predict it and go see the next one. And having seen a solar eclipse myself, I would have to. I remember, well, on the one hand, I remember thinking, really, that's it after 2 minutes? But at the same time, my next thought was, how in the world can I get to the next one? And yes, they are amazing, and because they're based on the movements of the sun and the moon, they're also predictable. And so they require mathematics to predict them. And so not just science and so there's something to be said that we have all of our civilization because people wanted to predict solar eclipses, and that gave us Kepler and Newton and Newtonian mechanics, and then the alternative geometries that Frederick Gauss and others had discovered enabled the possibility to ask ourselves, what about time and space? And enable us to discover a theory of relativity and how it which is important for describing the real world. Which is an interesting thing about mathematics, that a lot of times mathematics is first discovered abstractly, and then it feeds us. It's then borrowed to help us discover new things about the universe, which is kind of an interesting thing for something that might not be connected to reality. I just have to point that out. And finally, quantum mechanics, and this is a picture of Schrodinger's cat. Quantum mechanics has gone so far as to combine weird things like probability theory and imaginary numbers to describe how particles can be waves and not waves at the same time. And it's again very important to be able to understand if you want to create circuits which has tiny electrons passing through them, but at the same time seem to contradict relativity in big ways, yet still interact with it. And this is actually each of these also represent represent a reminder that these kinds of things actually go both ways. That while it may have taken several decades to do this, and this is something I recently learned about, mathematicians have been taking quantum mechanics and have been generalizing it in ways beyond physics, just to see what the mathematics of physics is, or what the mathematical assumptions of quantum mechanics can lead to. And so relativity, or so basically, physics and engineering and mathematics all this have this way of just going and doing their own things. Sometimes in such ways as looking back and saying, wait, is that even possible? Is that even valid? And then sitting down and proving and say, yes, maybe it is valid. So all this has a very interesting way of all interacting with each other. Now I wanted to mention a few books for suggested reading. The first things are books I've read myself, or at least in part, and I could highly recommend. The Philosophy of Mathematics in particular I want to point out because I read this in preparation for this presentation. And it's a good summary of mathematical thought, and it's actually written by someone who considers himself a Platonist, and his goal is to try to prove that that you could use pictures in mathematics, and it's just as legitimate as using lexical arguments, and that even lexical arguments which have been used in an attempt to get away from the informality of diagrams and to try to get away from the imperfections of diagrams can lead to their own contradictions, as Russell's paradox shows. And The Emperor's New Mind is a great tour of physics and mathematics, and Journey through Genius is a great tour of interesting mathematical theorems. But the remaining books are actually written with kind of with I don't like the term layman, but written with the casual reader in mind who wants to get a good an interesting feel for what mathematics is like. And while some mathematicians don't like chaos making a new science in particular, I have to point out that it may not be the most rigorous and mathematical things, and it may be describing mathematics that ultimately is pointless in the long run. But nonetheless, it was one of those things that opened my mind to mathematics and really helped me to appreciate the mathematical world. The next set of books are also are books that I haven't personally read, so I can't vouch for them, but I would like to read them. And these are also intended for a popular audience and for casual reading. And finally, I wanted to mention Ed Berger, who opened my mind to how all of this, not just mathematics, but all of civilization started with a bunch of shepherds wanting to keep track of sheep. And while I don't think his colloquiums are online, I do know that he's written some books, and I'm kind of curious to know if he's discussed the history of going from sheep to modern mathematics in one of those books. And one video is called "Do Numbers Exist?" describes some of these, two videos, "Do Numbers Exist?" and Platonism versus fatalism or formalism goes into some of these ideas a little bit more. But again, it's more of a summary than as an all-out dive into the things. And I would recommend Numberphile in particular as a fun YouTube channel that goes into all sorts of mathematical ideas. And so with that, I would like to conclude my presentation. And I hope I haven't gone over time. Thank you. Unfortunately, I don't have time for questions.